Hello everyone, my name is Reza Hosseini. I'm from University of Sydney School of Computer Science, Center for Distributed High Performance Computing. I'm going to introduce our recent project, which is called Q-Flink, which is a QoS-Aware controller for Apache Flink. This work is jointly done by Dr. Ali Jannisari from Iowa State University, Professor Javed Taheri from Department of Mathematics and Computer Science in Karlstad University in Sweden, Dr. Wei Bauer, Professor Albert Zumaya, both from University of Sydney, and Professor Zahid Tari from RMIT University in Australia. If I want to give you an overview of what is Q-Flink about, Q-Flink is a controller that we designed based on MPC design principles that tries to solve problems for Apache Flink, for stream processing engine called Apache Flink. So Apache Flink is a modern and very powerful stream processing engine that can process data, can process continuous data, which we call it streaming processing, in a near real-time fashion. So developers can submit some query or some functions that continuously process over data that come to the system. So this is very different from batch processing, which you may find or are already familiar with, like Apache Spark or MapReduce paradigm, which there are a huge amount of data that stores in disk, and then developers run the function over those, or run some functions over those batch processing. So in stream processing, we don't have batch of data. So because of that, we need to somehow introduce the concept of time. So you need to define, or the developers need to define a window, sliding window. So over that time, the processing must occur, or you just interested in processing that occur on that windowing sliding window time, which is the recent data items, like for example the past 5 minutes or past 5 seconds. You just want to run your functions. And to increase actually the throughput of your system, you normally don't wait for 5 seconds or 5 minutes to gather all data and then start running your functions. So you normally divide this sliding window to smaller window, which we normally call pane. And during this pane, we normally run some functions or some functionality. So that's called actually pane-based aggregation. So these panes are a smaller part of a sliding window, and you normally start running every W seconds, which is the size of your pane. So normally in such categories, you normally divide, or actually the developers need to provide two types of queries or subqueries, which we sometimes call pane level and window level queries. So this is the functionality that you want to run where your data. For example, if the window size is 5 seconds, developers can define pane size as 250 milliseconds. So every 250 milliseconds you run a pane level query, and then every 5 seconds you run a window level query. So this is actually a big picture of what we're doing and then what's happening inside the Flink actually. So we have some workers, which we call it pane level worker, and each worker has a pane buffer, and you can actually measure the size of this pane. And also we assign, or we define actually per worker or per machine one buffer, and per application you can also define one buffer. So in here you can see that per application you have one buffer, and then there is a tuple emitter that sends data to each pane, and then you can also measure the pane the pane buffer per application. And then the pane results can be gathered and then aggregated, and then go to the window level query, and then further process for the window level query. But the good thing is that we can measure actually all of the size of all of these queues, and actually this helps us to design or control. So the existing resource allocation policy in Apache Flink doesn't respond well to varying arrival rate for each stream. And also when the physical resource condition change, like for example, if you have a bottleneck in your CPU, or if you have a lack of memory, or if you have a high or low throughput in each machine, the existing actually resource allocation in Flink, or even in Apache Spark streaming, doesn't understand this and doesn't respond to that. In addition, this approach, or the existing approach, are not very concerned about the shared resource interference, and this is actually important when you have multiple applications that try to use the same resource. For example, if two applications are running in the same CPU, and then because of the operating system device time slice for this application, so when this context switch happens, then the cache of one application, that cache that stores data for one application, can be evicted from context switch operation by operating system. So this is normally referred to shared resource interface, or shared CPU cache interface. And the same thing can happen for memory buffer for each when you have multiple applications running the same machine. The other limitation of existing resource allocation is that they are not aware of quality of service for each application. So if you have, if you provide the user this ability to define the quality of service, for example, some applications are more important than others, for example, in terms of response time, then the existing RA in Apache Flink cannot actually provide such mechanism for you to define such quality of service. So motivation of our work is actually to address such gap. So first we define, or we actually develop a resource allocation Flink engine, which also can be used for Spark streaming engine that responds to runtime behavior. So if the resources is overutilized or underutilized, then this underutilization or overutilization can be evaluated by our controller. And also it provides a mechanism that you can the user can define the quality of service. So the controller actually respects such quality of service. And as I mentioned before, the round-robin strategy cannot respond well to temporal change in the incoming traffic per application. For example, if you have two types of application, one of them is highly important for you, the other one is not much important for you, then if you change the rate for the low priority applications, if you increase actually the incoming rate for low level applications, so definitely it affects the performance of high priority application. And actually we designed the control in such a way that it copes with such problems, it addresses this problem. And the main advantage, or the main pivot of or approaches that we design a model predictive controller that I'm going to explain this this slide. So in this approach that we choose, the MPC, which is very famous in other disciplines, engineering disciplines, so it tries to look at the past, the history of what happens in your system. You define a target for your system. For example, in our case, the target can be the response time for every application. And then the MPC, the controller, tries to measure the difference between the target value and the existing value. So the red color here shows the target value, and the orange color shows the existing value, the existing performance value. And then such difference shows that, okay, the controller needs to do some action such that this difference becomes zero, or get closer to the zero. So the controller do some actions, which is actually based on some system models that they already defined. Then the controller applies such actions to the system, but the controller applies these actions such that in the future tau or future p horizon, future p epoch, such change effects. So it gradually actually tries to minimize such a gap between the target and the predicted and the measured output. So in our model, the main components of our model is that we develop a system model that predicts the behavior of each buffer and the response time between stream processing. Actually, we use a very famous GGMQ approximation, which introduced by some scientists 30 years ago in mathematics and performance model. And this actually give us a very good estimation of the average waiting time of data tuples per pane and per stream. We also use a forecaster, a predictor that tries to predict the change in the rate of data that comes to the system. So you can actually use very simple predictor like Kalman filter, or very complex one like ARIMA. So they're exchangeable actually in our model. So this actually gives you gives the controller an estimation of arrival rate for the future value. And then we also define optimizer that tries to decide how much capacity of each CPU share or memory share must be assigned to each application. So it actually tries to develop a problem called budget problem. So you have a limited budget, and then you want to assign it to different projects with different priority, and then it tries to solve this optimization problem. And for us, the optimization problem tries to minimize the total cost of service violation between all applications in all distributed computing systems, and also it tries to avoid shared resource interference based on some measurements of memory bus read and write rate. So we implemented and evaluated actually the effectiveness of our approach by comparing it using round robin, which is the default resource allocation policy which is employed by Apache Flink, and also another approach which is called class-based weighted fair queuing that tries to define some constant queue, and then each queue has its own constant share of CPU. And we also develop or actually use some synthetic data sets that are already used by many researchers in this field, which is called DPIP and GSM, which actually mimics some important information over streaming data. And we define also two different periods called non-burst and burst period. In the non-burst periods, the capacity of shared applications are enough to process all streaming data and reach to the target value, which is defined by users. But in the burst period, there is limited amount of shared resources, and normally the traffic in the burst period, we increase the traffic rate for application belonging to the lowest level quality of service level. And here I just show some examples of the results, and you can see here in the burst period and non-burst period, the 99th